All right, we are now recording. So welcome to the online physics class for May 1st. Let's go ahead and jump right in unless anybody has any questions. Every time I ask you that, you always no. So we'll go ahead and start right into it. Okay, so question number 1 from the quiz. Why is the work of Louis de Broglie important? He is the one that proved that all matter is made of waves. Everything in the universe, electrons, protons, photons, well, we already knew about photons, but electrons and protons are also waves just as much as photons are, which changes everything. We're going to start today to talk about it, and then on Monday we're going to continue more. That totally changes everything about the whole universe. That opens up the door to relativity as well, which a lot of people think is an unrelated topic, but it's actually very closely related. If it weren't for quantum mechanics, relativity and all the weirdness of relativity would not happen. Okay, so that's pretty important. All right, so if you want to see electrons behave as waves, if you shoot them through a diffraction grating, well, if that diffraction grating is the same size as the ones that Thomas Young used, you're not going to see wave-like properties. You're not going to see diffraction because the wavelength of the electron is even smaller than the wavelength of light by a long ways. So it's going to go shooting through those little slits just the same as light goes shooting through a great big window. And you're going to see sharp edges. You're not going to see diffraction. You're only going to see the diffraction if you make the openings be super small, like on the atomic level. And so you're going to have to use like a crystal in order to do that. Okay. All right, so the Compton effect, well, that one's, if you've got a photon coming along which has no mass, and therefore you would think it would have no momentum, right? And it hits an electron, it can give momentum to that electron. Okay, so what that means is that the photon actually does have momentum. Even though it doesn't have mass, it does have momentum, which I know is really weird, but that's the way it goes. So Jaron is saying make them move really fast, but it wouldn't have to be really fast. Well, actually, the faster you make them move, the shorter the wavelength. Okay, and the shorter the wavelength. Okay, I misread it. Okay, so or make them move really fast, but that would have to be really fast. No, it's just okay. So the faster you make those electrons move, the shorter the wavelength is going to be. And so the less noticeable the wave properties of the electron are going to be. Okay, so let's move on. Okay, so is it just a coincidence? So on the one hand, we got light. And so we do experiments with light, and the proportionality constant works out to be 6.63 times 10 to the negative 34. And then on the other hand, we have matter, which up until then were thought to be two totally unrelated things. And when you do experiments with matter, you get the same proportionality constant, 6.63 times 10 to the negative 34. Is that just a coincidence? No way. There's no way that can be just a coincidence. So that's what tipped us off to the fact that there is a connection between energy and matter, a connection that we had not previously suspected. Okay, and the secret word was, of course, Caesar. All righty. Okay, let's look at last night's homework. So here are the answers to the problems that you haven't already looked up in the back of the book. There were only like a very few that you could look up in the back of the book this time around. So I'll give you guys a minute to look at those. And let me know if you have any questions. 21 and 22. Okay, so let's do 22 first because that's the first one you asked about. Okay, so hang on while I get my glasses. Which one is 22? Okay, so the kinetic energy in problem number 3 has a de Broglie wavelength of 0.14 nanometers. What's the kinetic energy? Okay, so let's see. Let's go to share the whiteboard here. Okay, I trust you can all see just an empty whiteboard right now. Okay, so if we've got an electron that has a de Broglie wavelength of 0.14 nanometers, okay, so we know that lambda equals h over mv, and so um, uh, let's see. So if we know the de Broglie wavelength and we know the mass, so then we can figure out what the velocity of that electron is. And so that means we can figure out what the kinetic energy of that electron is. So let's just rearrange that. So we're going to have V equals H over lambda M. Okay, so we know H, they tell us what lambda is, we know what the mass of the electron is, so we can figure out what the velocity of that electron is. And we know that the kinetic energy is 1/2 m, that's an m. It may not look like an m, but that's an m, v squared. Okay, so we just take that and plug it into there. We know there. So you agree that we can figure out what the kinetic energy of that electron is? All right. And so now we want to know what is the kinetic energy of a proton that has the same wavelength. Okay, well, same type of thing. Okay. Um, so this time it's a proton. So the mass is going to be different. Okay. But that's okay. And so basically just do the same math as before. So they're saying that the proton has the same wavelength, so lambda is the same. The mass is different this time, but h is obviously the same. So that means we can figure out what the velocity of that proton is. And so then come over here, take that velocity, stick it in there, and bingo, so we can solve for the kinetic energy of the proton. Now, one catch is that whenever you're using these equations, they're always going to come out in joules. Okay? All right, and they are asking for the kinetic energy in electron volts. Okay, so you know that 1 electron volt equals 1.6 times 10 to negative 19 joules. So you should be able to just convert it into electron volts from that. So Ellie, does that answer your questions on number 22? Okay, good. And so Maddie wants to see 21. So 21 says, what voltage is needed to accelerate an electron to give it? Okay, so let's clear this out. Okay, so we want the electron to have a wavelength of 0.125 nanometers. So again, we're going to start off with this. So we know that lambda equals h, that's an h. Okay, terrible looking h. Let me try that again. Okay, so lambda equals h over mv. Okay, so we got to do basically the same thing. They tell us what lambda is and it's electron, so we know what the mass is, we know what h is. So we need to solve for velocity of just like we did before. So v is going to equal h over m lambda. Okay, so so if they tell us the wavelength, we can figure out what the velocity is. And so then we say, okay, well, what voltage is needed to do that? Well, we know that Q times delta V equals the work, which is equal to kinetic energy. Okay, so if we know the velocity, then we can just 1/2 mv squared, that will be the kinetic energy. So we can figure out what the kinetic energy is. We know what the charge of an electron is. So bingo, we could figure out what delta V is. I did that pretty quickly. But Maddie, does that answer your question? Okay, good. All right. So are there any other questions about any of the other problems? Let me go back to the screen that has the answers on it. Okay. 27. Okay, yes, 27, I definitely intended to discuss that one. In fact, I've got a whole bunch of slides that give you some background information because you need to know the background information. So I'm going to go over 27 and I'm going to go over it in great depth. So let's hold on for that one. Last chance, are there any other questions before we start into 27? Okay. All right. So let's go into 27 then. So what are they asking in 27? Let me make sure I get the wording exactly right here. So they're asking about the Heisenberg uncertainty principle, basically. So basically, they just want to see if you understand the Heisenberg uncertainty principle. And I know from previous experience, the students usually do not really get it. I mean, there's always a few students who could tell me what it is. You know, they could quote Heisenberg's uncertainty principle, but to actually explain it and explain why it's there, that's the important thing. All right, so let me just go over a few bits of background information that you need to know before you have any hope of understanding Heisenberg's uncertainty principle. Okay, so I'm going to start in a very unusual way. Uh, what you see on the screen right now is one of my favorite books. When I was in high school, I somehow got my hands on this book that's titled How to Lie with Statistics. And it's one of the best books I ever read. It's really good. Basically, it talks about how you can manipulate statistics and especially graphs, so that if there's some point that you want to make that you want to make it appear more important than it really is, or maybe some other person is arguing against you and you want their argument to appear less important than it really is, there are ways that you can manipulate statistics uh, in an unethical way. And politicians, oh boy, do politicians ever do this all the time. So that technically you're not lying. You know, if somebody were to take you to court of law and accuse you of lying, you could, with full plausibility, you could say, well, I wasn't lying, but you were definitely misleading people. Okay, so it's a great book. I have a copy of it in my room. I highly recommend you guys read it. It's a wonderful book. Now, the reason I bring it up is because I have always been tempted to write a book called How to Swindle People Using Quantum Mechanics. And really the reason, the motivation for this was I once saw a movie where I'm going to show you bits from that used quantum mechanics in order to swindle people. Okay, so let's talk about how to swindle people in general. Okay, so first off, you guys, I'm sure you've heard the term con man or con game. Okay, so con is short for confidence. And so the way that a con man works, or the way that a con game works, okay, is first thing you do is you do something that's really good, something that's really well done, that people look at it and they say, oh, wow, boy, this guy really knows what he's doing. He's good. So because you did something really good, you've gained the confidence of your intended victim. Okay, so once you've gained their confidence, then you ask them to trust you with their money. And once they give you the money, you take the money and run. Okay, so the important part is step one, gaining their confidence. Now, what has that got to do with anything that we're talking about? Well, what you see on the screen right now, this is the movie that I saw many years ago, and it is a total con game. Now, if any of you, if your parents have seen this movie, I'm, sorry, but that's what it is. Almost every year, there's always somebody who says, "Hey, my mom, she loves that movie," or "My dad, yeah, he's in." So if any of you are in that case, I apologize, but it is a con game. It's a swindle. But the neat thing is, okay, step one of the confidence game is to do something really well to gain people's confidence, right? Okay, so this movie, they do one thing at the very beginning of the movie that is really, really good. And what that thing is they have a little cartoon-like video. It is a cartoon, not just cartoon-like, that talks about quantum mechanics and how quantum mechanics works. And it's really well done. And so I'm going to show you this video that these people put together. It takes just a couple minutes. This is the cartoon. I'm going to start it in just a minute. Now, they're going to talk about the double slit experiment, which is something we've already talked about before. And so some of you are going to say, well, we've already talked about this. Well, be patient, because they take it to the point where we left off, and then they go on to the next step, which is something that we have not talked about, something that is very important. So let's sit back and let's watch this thing that these con men put together that is really good. And I can understand why people would trust them, because they really do a good job here. So let's sit back and let's watch it. Let me make sure that my sound is turned on. In order for you guys to hear it, I need to, okay. All right, so if you guys can't hear the sound when I click play, please speak up and I'll go back and restart it, but you should be able to. Okay, here goes.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment.
Can you hear?
To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity.
Oops, didn't mean to do that. Oh no. It was my intention to just pause the video. Okay. All right, so what you're seeing here is diffraction, of course. And okay, so when you look at that line in the middle there, okay, you see that one bright line, but you see it's got really fuzzy edges, and you can see that the light is spread out here. But if you just focus your attention on that line, it looks kind of sort of like it would if you were shooting marbles through there, okay? But what happens next? Come on. Okay, I don't know why. When I practiced this before, I could pause the video all I wanted and it didn't cause any problems. Tell you what. Oh no, Microsoft PowerPoint is not responding. Okay. All right. King Crimson eradicated the time we watched the video and left past it. Okay. All right. Tell you what. Let me stop the video and come back and restart it. Okay. Because there's a lot of really good stuff here. So what I'll have to do. Deep breaths. Yes. Right. Okay. All right. Here we go. Okay, so it has restarted. All right, this time I guess when I start the video, I'll just have to not pause it. Okay, here we go. All right. Okay, here we go from the beginning, sorry.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum.
Now when he says let's go quantum, he means we're going to shrink everything down to the atomic level.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through.
This is the important part. Watch this.
They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay. Now, it's really unfortunate that I wasn't able to pause the video, and I don't dare do it again because I don't want to crash PowerPoint. But there were a lot of places in there that he said things that were super important. Okay, so the first thing that I think is really important to emphasize is that scientists really did devise a way to where they could shoot the electron through the double slit one electron at a time. Okay, because there were people who were saying, well, okay, well, maybe we got two electrons going through there and they're bouncing off in funny ways. That's explaining it. So they shot the electron through there one electron at a time, and they still saw the diffraction pattern. Okay, so there's no way that could happen if the electron was a particle. A particle can go through one slit or the other. A particle cannot go through both. Only a wave can go through both slits at the same time and then interfere with itself when it comes out on the other side. Okay, and then the last thing at the very end there, he said that the observer collapsed the wave function by observing. So what he's talking about here is the fact that scientists, they were curious, to see if they could figure out what's going on. So they put measuring devices on each of the slits so that they were able to see which, is the electron really going through both slits. And when they did that, the diffraction pattern totally disappeared. What happened was it went back to just the two bands. So it means that when they measured the electron as it was passing through the slit, the act of measuring the wave caused the wave function to collapse. And what that means is the energy of the electron was spread out over an entire wave, but when the electron interacted with their probe, okay, the wave function, all of that energy, which was spread out all of a sudden, which was spread out all over the place, when it interacted with their probe, all that energy collapsed at one point. Okay, and then as it passed by that point, then it became a wave again. But at that instant that the interaction occurred, all of the energy collapses down to one point. Now, in my opinion, this right here is the weirdest thing of quantum mechanics. So if you look at the picture, you can see here, again, the wave collapse and how it works. So we've got electrons going through these slits here, and most of the electrons hit the wall and they collapse at the point they hit the wall, but some of the electrons make it through the slits, okay? And so they come out on the other side as a wave because they haven't interacted with anything, so they come out as a wave. They interfere with itself, and then when the wave gets to the board here, okay, the energy of the wave is spread out so it hits everywhere, but it doesn't interact everywhere. If you'll look right here on the screen, you'll see that what we've got is a whole bunch of little dots. So when this one electron comes through, remember we're shooting one electron at a time, right? So the electron comes through, goes through the slits, it hits the board, but it only interacts at one spot. So all of the energy that was spread out everywhere collapses and it all appears at one little point. So it might appear at this little point right here, or it might be this one here, or it might be this one here. We cannot predict where it's going to hit. All we can predict is the probability that it's going to hit. And so right in this region right here, there's a higher probability that it's going to hit. Over here, it's a less probability. And further out we go, the less probability. But in between the bright bands, there's zero probability. Okay, so we can predict with excellent results the probability of it hitting somewhere, but we cannot predict exactly where it's going to hit. Okay. This, in my opinion, is the weirdest thing about quantum mechanics, although there's a lot of competition for that because there's other things we haven't talked about yet that are also really weird. So I like to think of it this way. Let's say you've got a detector, and this detector is set up so that it will go bing when it sees an electron. So if you've got the electron, which is spread out over this area here, so this is the wave bundle that represents the electron. If you put the detector in the middle where there's the highest probability, then the detector may or may not see the electron. It may or may not go bing, but if you put it in the middle, that's when it's going to have the highest probability that it'll go bing, okay? If you put it out here on the edge, then there's a lower probability. And if you put it way out here, there's an even lower probability, but not zero. Because this wave function, you can see that it approaches zero asymptotically. And you guys know from mathematics that when something is approaching zero asymptotically, it never gets to zero, okay? Now it does get so close that, the probability of it is so close to zero that you might as well call it zero, but it is not zero. And this is going to come in really important a little bit later, okay? All right, so basically, okay, it is impossible for you to answer the question of where is the electron. All you can do is talk about the probability of finding the electron at various places, okay? And so this is pretty much the height, the heart of the Heisenberg uncertainty principle, okay? So delta X right here, which I hope you guys can see. I hope it's not covered up by your chat window settings. Okay, delta X represents the uncertainty in where the electron is. Okay, so because you cannot say exactly where it is, what you'd have to do is you have to talk about in terms of probabilities. So let's look at this graph right here. We know that lambda equals h over mv, right? So that means the higher the velocity, the shorter the wavelength. Well, it also means the more mass, the shorter the wavelength. So this is why Heisenberg really talked in terms of momentum. So basically, the more momentum a particle has, the shorter its wavelength. Okay, so what you see up at the top here is a particle that has high momentum, either because it's moving fast or because it has a lot of mass. Okay, and so because the wavelength is short, the wave bundle is condensed into a nice little packet there. And so if you want to say where is the electron, what you have to do is you have to say, well, give me a number for what probability you are willing to accept. So in the example here, I've said, okay, I'm willing to accept a 95% probability. So in that case, then you can say, okay, if you're willing to accept 95% probability, then I can do the calculations and I can tell you there's a 95% probability of the wavelength, or that the electron is somewhere in here. So if I take my probe and I stick my probe in here, there's a 95% probability that the probe will go ding. Now, if you look at a different electron here, an electron that's moving a little bit more slowly, or maybe it has less mass, okay, that means the wavelength is bigger. So if you look, the total number of wave peaks here is the same as there, but those peaks are spread out because the wavelength is longer. So now the uncertainty in where the electron is now bigger, okay? So if you ask me where's the electron, and I say, well, what percent do you want? You say 95%. Then I say, okay, you see how the range here is bigger than it was before. And then when we go even slower, the range gets even bigger. Okay, so there's a trade-off between momentum and the size of the wave packet, which could be described as the uncertainty as to the wave's location. So Jaron says with limits, it means as one increases, the other decreases. Yes, I agree with you there, Jaron. Okay, so you see here, this is one of the key tenets of quantum mechanics, is that you cannot say exactly where the electron or the proton or any other particle is. You cannot say exactly where it is. All you can do is talk about the probability of being able to find it. Now, this bothered a lot of people, okay? One person in particular, this guy right here, okay? Einstein really fought hard against quantum mechanics because in his gut, he just believed that you should be able to like take a picture of the universe and see where everything is, and then from that point on, you should be able to calculate where everything's going to go. Okay, so let's see. Hang on, there's a comment here. Okay, yeah, Jaron, I hope you don't mind if I don't read the comment, but yeah, I agree. I'm basically, that's it. Okay, so Albert Einstein really fought hard against quantum mechanics because he believed that God does not play dice with the universe, which is what he looked at when he said probability. But as time went on, and Einstein looked at all of the experimental data that people were gathering over the years, eventually Einstein changed his tune because the data was irrefutable. Okay, he looked at all the experiments that had been done, and after a while he said, well, I guess God does play dice with the universe because quantum mechanics works so well at explaining so many things that could not have been explained before. Okay, so Einstein did eventually come around and believe that quantum mechanics actually was real. Okay, now Einstein is not the only person who fought very hard against quantum mechanics. There's another guy who I'm sure that you've heard of. His name was Erwin Schrödinger. And like Einstein, he thought that quantum mechanics was just too crazy to possibly be true. And so I'm sure you guys have heard about Schrödinger's cat, right? Almost everybody, almost all students that I've talked with have heard about Schrödinger's cat, but very few people actually understand Schrödinger's cat. Okay, so this is a little cartoon here. So the cat's in the box, is it alive or dead? And his response is yes. What in the world does that mean? Okay, so I'm sure there's somebody out there who thinks they understand Schrödinger's cat. Here's a little picture that you can use. Anybody want to turn on their mic and take a chance at explaining Schrödinger's cat? Okay, so
Okay.
Jaron, okay, so that's you, Jaron. Let me just read your comment before you speak. So Jaron typed in, he's saying that Schrodinger was trying to prove that quantum mechanics was ridiculous, which is exactly right, I agree. So Schrodinger's cat was his initial attempt to prove how absurd quantum mechanics was. But later on, even Schrodinger came around too. Okay, so Jaron, you got your mic on? Go ahead and give us just a Twitter version. Just keep it down to about 30 seconds if you can. What's this whole deal with Schrodinger's cat?
Okay, so we have a radioactive thing, this isotope. If a single one of the atoms ends up, dissolving because of half-lives, this hammer will break a vial of poison, killing the cat. It's either poison or acid. However, the box is closed, so we never know if the vial breaks, meaning we never know if the cat is dead or alive until we open the box. Until then, we just have to assume the cat is both dead and alive.
Okay, that what you've stated is exactly the way that it's usually stated, and
I
most
know it's
students,
probably wrong.
no, what you said is correct. But most students, when they hear that, they say, "Huh," and they don't really get it. Okay, so let me take it to the next step. What I'm going to show you right now is, remember that video that I told you was produced by a bunch of con men? Okay, so this clip is from the middle of that video. So after they've established their competence, after they've done such a really good job of explaining quantum mechanics, then they come in with this part. Now there are two people you're going to see. The guy that you're seeing right now, who's got his eyes closed, he is a famous physicist. He is a real honest to goodness physicist, and he knows a lot about quantum mechanics. After he finishes, they're going to cut to another guy, and the second guy that you're going to see is one of the people who made the video, and he is going to make an argument which is pretty much what Schrodinger did. And so I'll turn it on and you guys can hear it for yourself. So the first guy, what he's going to say is completely true, and he's going to say it the way that a physicist would say it. The second guy, yeah, let's see.
We don't know in quantum mechanics how to hook ourselves as observers up with the world. We don't know how to treat ourselves as observers as just another part of the physical system that we're describing. The only way we know how to do quantum mechanics as it's traditionally formulated is to keep the observer outside of the system you're describing. The minute you put him in, you get all these paradoxes. And we're forced to say things in quantum mechanics like, look, the book is doing what it's doing because of quantum mechanics, and I see that because I'm there and I see it, and you better not try to analyze that second part of the sentence in terms of applying quantum mechanics to it, because it's going to break down. That's why there are these two separate laws of the evolutions of physical systems. One that applies when you're not looking at them, the other that applies when you are. But that's crazy.
There's no way that we're ever going to mathematize or put into mathematical formula this very act in which a conscious observer comes up with the answer. People say, oh, the measuring instruments, the recorder records it, and there it is, it's on the tape, it's recorded. You forgot one part of the equation. Somebody has to look at the tape. And until somebody looks at the tape, it ain't recorded at all.
Okay, so that is the argument of Schrodinger's cat. Okay. Now, physicists today recognize that quantum mechanics really is true. And so if you've got this event that's happening inside the box where maybe the cat is dead and maybe the cat's not, okay? And so this guy is saying, well, until you open up the box and look at it, until a human being looks at it, the event has not happened. Now, what that really is saying is that if you've got an electron that's a wave function, what he is saying is that the wave function does not collapse unless a human being looks at it. Okay, and so the cat won't die unless the wave function collapses. Okay, now this guy that you're seeing right here, he's one of the con men. Okay, so but he is stating Schrodinger's argument quite well. Okay, that the cat does not either become alive or dead until a human being looks at it. Now, my point of view and the point of view of pretty much all physicists, in fact, all physicists that I know today, is that last part of what he said is garbage. It is such an incredible, egotistical, vain thing to say that unless a human being looks at something, that thing is not real. You know, the wave function doesn't collapse unless a human being looks at it. What an egotistical, vain thing to say. Yeah, the universe exists, even if people aren't around to see it. The universe still exists. But that's basically the argument of quantum mechanics. Okay, so Josh is saying, is that why my computer finally loads when I look away? Oh, you made me onto something. Yes, as long as you keep looking at it, it doesn't load. Okay, so that's the argument behind quantum mechanics, which, as I hopefully made clear, this was an argument that Erwin Schrödinger put forward early on because he thought that it illustrated the absurdity of quantum mechanics. But even Erwin Schrödinger eventually came around, like Einstein did, because the evidence is overwhelming. Quantum mechanics works. Quantum mechanics describes the world. So this whole Schrödinger's cat thing, you know, it's really overblown. Okay, now there's one other thing that I think is really important we talk about in the movie here. I'm going to replay the last part of that first clip because we're not, well, I'm going to replay part of it, not necessarily the last part. Remember that first clip? The narrator worded something in a very peculiar way. And when I saw the movie, I heard what he said, and I said, why would they word it in that really strange way? So let's play it again and look at the way that he worded it. And I want you guys to see what you think about his choice of words.
The electron decided to act differently, as though it was aware it was being watched.
Okay, so he's saying the electron decided to behave differently as if it was aware it was being watched. Now, when I heard that, I thought, what? Now, technically, I can't call him a liar because, yeah, I can see where he's coming from, but I would never have worded it that way. I would have said the wave function only collapses when the wave function interacts with your probe. Okay, if your probe isn't there, the wave function doesn't interact, it doesn't collapse, and so it just passes on in its merry way. So when you measured it, you caused the wave function to collapse. Okay, so I wonder, why do you suppose he would have worded it the way that he did? Well, it all has to do with the scam. Remember, step one of the scam is to do something really well so you gain people's confidence. Step two of the scam is once you've got their confidence, you want to take their money and run, right? Okay, so they worded it this way because they want to move to step two of the scam. So here is a short clip that comes from later on in the movie. I want you guys to watch this, and you've learned a lot about science now and the scientific method. So he's going to describe an experiment that people do in their organization. He's going to describe this experiment, and I want you guys to look at it and give me your opinion. Do you think this is good science, or is this not good science? All right, so here goes.
We took two simple black boxes like this. Inside is a very simple electric circuit with a few diodes, oscillator, EEPROM, some resistors and capacitors. Basically, that's it. We wrap one in aluminum foil. We put it in an electrically grounded Faraday cage. The other we set on a tabletop around which four very well qualified meditators, highly inner self-managed individuals sit. And they go into a deep meditative state. They cleanse the environment. They make it essentially a sacred space using their mind cleansing procedures and their intentions. And then one of the four speaks the specific intention for this device. The intention is to influence a particular target experiment. Might be to increase the pH of purified water by 1 full pH unit, or to decrease the pH by 1 full pH unit. We've used these devices on all those experiments and have been robustly successful. In the meditative process, then after one speaks the particular intention, it's held various ways by the four for maybe 15 minutes, and then so be it, it's let go. And then a subsidiary intention is stated to seal that imprint into the device. We take one of these devices with its aluminum foil, we put it in a soft package, we put it in a FedEx packet, we ship it 2,000 miles away to the laboratory we were using up in Minnesota. And as soon as it arrives there, it goes into its own electrically grounded Faraday cage. The next day we do the same with the control. The experiment is running, and basically then one just takes the device out, sets it beside the experiment within 6 inches to a foot, and turns it on for a period of time. That's it. Now, we learned over some period of time that there was another factor. We found that the use of these, we call them intention imprinted electrical devices, the continued use of this somehow conditions the space to some higher level of symmetry. And we start getting new phenomena. That is, the devices work. That is, the pH, which is normal, starts rising 1 full pH unit, if that was the imprint, or starts dropping. If you go 1 full pH unit or beyond, you're dead. I mean, that's what it means to a human.
Okay, so let me just summarize what this guy just said. He said that they invite people to come to the place where they meet, and they do this experiment where they sit around the table, and they have 2 of these little boxes with a bunch of random electronics in them. One of the boxes they put in a Faraday cage. Do you guys remember a Faraday cage? That was something from one of our previous quizzes. Remember the tinfoil hat, right? That's a Faraday cage. All right, so the reason they claim that you need to put it in a Faraday cage is because they got these 2 devices, and one of them they want to be a control unit. You guys know when you do an experiment, you want to have a control, right? So the one that's going to be the control, they put that in a Faraday cage so that their thoughts cannot be absorbed by this other unit, the control unit. Okay, and then they take the second unit, which is the one that they are actually working on. They set it on the table, and they sit around it, and they think at it. Okay, and they think, increase the pH, increase the pH, increase the pH. And then this guy is claiming that when they send it off to their lab in Minnesota, 2,000 miles away, and the people in the lab turn it on and set a glass of water next to it, that the pH actually does what they wanted it to do. The pH either goes up or it goes down. Okay, so what do you guys think? Is this does this sound like a well-designed scientific experiment? I'm sorry. Thank you, Dean. You just earned yourself some bonus points there. What a load of bovine excrement. Okay, now why do you think it's bogus? What is it about the experiment that tips you off to the fact that this is bovine excrement, this is by the truckload? What is it that tips you off here? Sending thoughts and prayers to pH, okay. But there's one thing that to me is just a huge red flag that anybody with a high school science education should be able to recognize the huge flaw in this experiment. And it's not the idea of the experiment. I want to keep an open mind. I would love to believe that it's possible that you can think at something and your thoughts cause it to change. And by the way, because they've already played the first part of the video, remember how they said that the electron behaves differently when it's being watched? That's why they chose those words. They were setting up for this. What they're saying is quantum mechanics proves that electrons behave differently when they're being watched or when they're being thought at. And so this is an experiment where they claim it proves that the human mind can affect matter. And Jaron is saying, yes, it does. You know, that's how we move. I agree with that. Nobody has yet piped up with the huge flaw. There's one flaw that is just so huge that usually every year that I talk about this, somebody speaks up, and it looks like nobody is speaking up. Okay, so let me ask you. You guys have all taken chemistry, right? When you took chemistry, did you measure pH? So, yeah, yes, you guys, let's see a few more. Okay, so everybody's saying yes, they measure pH. Now, when you measured pH, did you have to ship it off to a lab 2,000 miles away, or were you able to measure the pH right there very easily? How did you measure pH? Yeah, how? But how? How did you do it? pH paper, yes. Litmus paper, okay? This is something that anybody with a scientific, even a high school science background, when this guy was describing this experiment, I would hope that you guys are standing up and say, bogus. If you want to measure pH, why the heck are you sending it off to a lab 2,000 miles away? I mean, the right way to do this experiment, I want to be open-minded. I want to admit that, you know, maybe the human mind can affect pH. The right way to do the experiment is not to send it off to a lab 2,000 miles away, okay? And this little electronic device that they talk about, what in the world has that thing got to do with anything? You take that thing and throw it in the garbage, okay? The right way to do the experiment is to take the water, set it on the table, and all of your highly experienced meditators can sit around the table, they can hold hands, they can sing kumbaya, they can do whatever they want, and then at the end of it, take the pH paper, stick it in the water and see what happened. That is the way to do the experiment. So why do you suppose they ship it off to a lab 2,000 miles away? What's their reason for doing that? To sound fancy? There's a more important reason. It's so that you can't be there to watch the testing. You just have to take their word for it, okay? If you did this experiment right, you would be able to see it with your own eyes right there. But because they've set this thing up in this unnecessarily complicated way, you just kind of have to trust their word. And you would be amazed at how many people have fallen for scams like this, especially in the state of Utah. Are you guys aware that the state of Utah is the number one, or maybe I should say last? I mean, more people in Utah get scammed than in any other state. What you're seeing right now is a newspaper article. I took it from the Deseret News a year ago. And they were asking the question, because everybody was saying that Utah is the fraud capital of the United States, and the Deseret News wanted to know if that was really true. So they have a great article here about an attorney who looked at the data, and if you run it on a per capita basis, Utah is far and away the worst place where gullible people give their money away to con men in schemes kind of like the one that you just talked about, okay? Now, I don't want to talk about any speculation as to why. You know, I do not want to have that conversation. But according to Deseret News, it's true that more people in Utah are gullible enough to fall for schemes like this than in any other state of the union. Okay, so I would hope that you guys would not be so gullible. You know, one reason why I like to say let's not take the book's word for this. Let's derive this equation. If we can't derive this equation, then we shouldn't believe it. Or if somebody tells you the Earth is round, you know, if they can't provide evidence for why it's round, you should be skeptical. Okay. You guys know that the AMES SWAGs, the Stool-Wide Achievement Goals, one very important one of those SWAGs is critical thinking. And this is, now critical thinking, a lot of people think it means just being able to work through a difficult physics problem or difficult math problem, which is one definition of it. But the other thing is being able to recognize when somebody is BSing you. Okay, that's critical thinking. And that's something you guys really need to be good at. Don't just take somebody's word for it. When they tell you something, you look at the evidence, okay? But anyway, okay, let's move on. Okay, so how are we doing for time here? Okay, we got about 5 minutes. I think that should be perfect. Okay, now there's one other thing that's really important that I want to talk about today that you need to know. Remember how I said that when you take the probe and you stick the probe at various places, all you can predict is the probability that the probe will go ding. And if you take the probe and you stick it out way out here where the wave function has decreased exponentially or decreased asymptotically, and it's really, really close to zero, but it's not zero. It may be small, it may be really small, but it's not zero. This leads to a really weird thing in quantum mechanics that a lot of people thought made no sense, but has been proven to be true. And in fact, it's very, very important for modern electronics and modern computers. Okay, there's this thing, this concept kind of is called particle in a box. Okay, so let's say that you've got a particle, and so according to classical mechanics, everything is particles, right? Not waves. So if you've got a particle and it's inside of a box and this box is really strong, then according to classical mechanics, this particle cannot get outside of the box. The amount of energy that's needed to break through the wall is more energy than this ball has. So according to classical mechanics, that ball cannot get out of the box. But according to quantum mechanics, it's not a particle, it's a wave. And the wave function decreases asymptotically to zero, but never reaches zero. So the little tail here of the wave function extends outside of the box. And if there is something else outside of the box which interacts with the wave, there is a very small but non-zero probability that the wave function will collapse and all of the energy, all of the thing that makes an electron will collapse and it will reappear at this point outside of the wave or outside of the box. Okay. Now it may only happen 1 in a billion times. Okay. But it it can happen, and in fact, it does happen. We're going to talk in just a minute about the fact that it does happen. So according to quantum mechanics, it is possible for an electron to get out of a box that classical mechanics says it could not possibly get out of. Okay, this is called quantum tunneling. Okay, I'm sure some of you have heard that expression. There are lots of science fiction movies where they talk about quantum tunneling, and they use that as the explanation for how the hero is able to magically disappear here and reappear there. They say, oh, it's because of quantum tunneling, and they never really explain it. Okay, and there are lots of flaws with that argument, by the way, but I don't want to go into it. So you see here, this is called quantum tunneling, and it's one of the strange predictions of quantum mechanics, but it's not just a prediction. It's actually been proven to be true. And in fact, you guys use it every day. Okay. Does this look familiar? This is our computer memory chip. This was the one that we talked about last time. It's called a DRAM. Okay. And those of you that have taken computer science class, you hopefully remember that there are different types of memory depending on what you want to do with it. So DRAM is used when you need something where you're going to do a bunch of calculations and you need to store intermediate values, and you don't need to store them for more than a couple of microseconds, but you do need to store them temporarily. Okay, and you're going to come back a few microseconds later and then you're going to use them. Okay, so when speed is critical and you don't need to worry about storing the data for a long time, then the kind of memory that we talked about last time, DRAM, is perfect for that application. But it's not good for long-term storage. Let's say you put a digital one in the capacitor here, and then you go away and you leave it for several days or weeks or years, okay? That data is going to bleed away, okay? These charges, they can work their way through into the semiconductor and they can bleed away. So it's not good for long-term storage. So for long-term storage, instead of using DRAM, you want to use a different type of memory. And one type of memory that is very commonly used right now is called flash memory. Okay, and so what you're seeing here is a flash memory cell with one little modification that we'll talk about later. So you look at this region right here, the gate region. Okay, let me go back here to the DRAM. You remember, so this piece here, this is a piece of metal, and there's an insulator underneath it. But if you go to flash memory, it has two pieces of metal separated by a very thin insulator. Okay, so what I'm going to do is I'm going to zoom in on this area right here. Let's take a closer look at that area right there. Okay, so if we connect up the electrode to the upper metal layer and we put a bunch of electrons on there, okay, can those electrons get through that barrier layer and into the buried metal underneath it? Can they get into there? Well, classical mechanics says no, okay, because this is an insulator and it's a very good insulator. Okay, so according to classical mechanics, these electrons cannot get through the insulating layer into the buried metal. But according to quantum mechanics, they can, because quantum mechanics says that they can tunnel their way through there. Now, not very many of them will. It might only be 1 in a billion, but that's okay because you can put lots and lots and lots of electrons on this upper metal. You can put trillions or even quadrillions of electrons on this upper metal. So even though the number of electrons that tunnel through might only be 1 in a billion, you'll end up with a substantial number of electrons down there, okay? And so then when you, and so then this is where we're going to store the digital 1 or the digital 0. And we're not going to use the capacitor that the DRAM used. We're going to let this buried gate, that's the place where we're going to store the digital 1 and the digital 0. So now when we open up this connection and let all those charges bleed off, these guys here can't get out. Now some of you are going to say, well, wait a minute, if they've tunneled their way in, then they can tunnel their way out. Yes, but if it's only 1 in a billion, the tunnels their way out, and there aren't that many of them to start with, then yeah, those charges are going to stay there for a long time, even though 1 in a billion will tunnel its way out. Okay, the rest of them won't. So you can put data onto a flash memory chip or a stick or whatever, and it'll stay there for years and years. Now, it won't stay there forever. It won't stay there for centuries. Okay, but it will stay there for years for sure. Okay, and one other really nice thing here is that because we're storing the data here, we don't need the capacitor anymore, which makes it so that we can now make our data storage devices a lot smaller, so we can cram a lot more of them onto the same size chip, so we can store more memory. You know, modern flash memory, they're able to store billions of ones and zeros on a little piece of silicon chip no bigger than your little fingernail, because they can make these so incredibly small. Now you might wonder what is going on underneath here. Why do we still have the channel and the charges flowing through the channel? Okay, the reason for that is because you need some way of being able to read whether there's data stored or not. You know, let's say we've stored, on some of the devices we've stored a digital 1, and on some of the others we don't. We got a digital 0. So we want to come in and we want to read the data to see, you know, what we've got stored. So we need some way of knowing, is there a digital 1 stored in there, or is there a digital 0? So if there's a digital 1, so if there is charge in here, then we're going to have charging by induction down in the channel region. And so if we put a charge here, we'll see that that charge will flow right through. So if the charge flows through, then we know we've got a 1 in there. If the charge does not flow through, then we know we've got a 0 in there. Okay, so this the channel on the bottom still plays an important role, but the data is being stored here in the buried gate. And the important thing here is that if it weren't for quantum tunneling, this whole thing wouldn't work. So quantum mechanics is the key to how flash memory works. And there are other things that it's the key to as well. But we are running low on time. Oh my goodness, we're a little over time. Okay, so I'm going to cut it short here, or I'm going to cut it off here. So today's a Friday, and you guys know that I try not to give you homework on a Friday, so I'm going to do that again today. Except, of course, for the daily quiz. The daily quiz does not count as homework. So give me about an hour to get the daily quiz, or get about an hour to get the video processed and then put it online. And so you'll be able to take the daily quiz in about an hour. Okay, so are there any questions, comments, or anything? Okay. No questions, no comments? Oh, okay, secret word. Okay, yes. So George or Peppa Pig fame. Oh, George of Peppa Pig fame. Okay, well, all right, I'm willing to go with George. Okay, so there you go. The secret word for today is George. All right. Okay, so have a great weekend. All right, I don't see any more questions, so I'm going to turn off the recording. So going once, going twice, sold.